Welcome back, everybody. This is going to be the last of the more technical talks. We've done introduction to Julia, introduction to differential equations and plotting, and this is essentially introduction to NeuroBlox from a technical point of view. So you will get familiar with the structure of the code in NeuroBlox and how you can contribute your own code to NeuroBlox, writing your own blocks and your own connection rules. And from the next session, so tomorrow morning, we will get more into the neuroscience. And I'm going to use all these tools from the technical sessions to do computational neuroscience in NeuroBlox. So what we will go through is essentially the structure of NeuroBlox and it's all of its design concepts, which the main ones are the blocks. The blocks are the components, and you've seen them as icons in the GUI. And now you will see how they look in code. And also the connection rules. The connections are essentially the edges of the graph, right? If the blocks are the nodes. These two things together essentially are the core in NeuroBlox. Exactly how I said before that types and multiple dispatch are the core in Julia. There's not one-to-one mapping because we will see custom types in both blocks and connections, but multiple dispatch is mainly exploited by connection rules. So, yeah, as I said, we have the types and multiple dispatch, and when I talk about types, I mean in particular type trees. Much like yesterday or on the exercises and on the presentation where we saw how number as a type in Julia is a super type above integers and above floating point numbers of any precision. So that is a small type tree. Exactly like that in Julia we have, in NeuroBlox we have type trees of all of our blocks. And every node in that tree could be either a primitive block, that is, neurons and neural masses, blocks that contain dynamics in them immediately. They could be composite types, so composite blocks, that's blocks that contain neurons or neural masses in them, so they could represent different circuits. And we also have some abstract types, where, as you saw in the exercise yesterday, you cannot instantiate an object that is an abstract type, but abstract types help us as some hubs in the type tree that branch out to multiple nodes, and it helps us to organize the type tree better, and they help with multiple dispatch. You will see how. So this is a partial view of the type tree that we have in NeuroBlox. Above all, the most general type that we have is this type called abstract blocks, and everything else, every other block is a subtype of this. And here I'm showing you 4 main categories that are subtypes of abstract blocks. We have neurons, neural masses, stimuli, and observer blocks. And then if we follow the tree down towards the leaves, neuron can be split into, and again, this is only a partial view, but we have, for instance, abstract XI neuron blocks, where we put all of our blocks that are explicitly excitatory in their dynamics. And likewise, abstract inhibitory INH neuron blocks for inhibitory neuron types. But we also have neurons that are just subtypes of neuron. There's no other node underneath. So like a LIF neuron, that's a leaky integrated fire neuron, similar to the generalized integrated fire that you saw in the exercise in the morning. That just falls under neuron. There's no other category here. And because this neuron can be used for both excitatory and inhibitory dynamics, it doesn't fall in any other of the two categories. But if we keep following the abstract categories, because in theory every abstract category is not a leaf in the type tree, it has to be followed by something else. Otherwise, there's no function for it. We have Hutchinson-Huxley neurons. That's the HH always in NeuroBlox. So I have a Hutchinson-Huxley neuron that is explicitly designed to be excitatory, and likewise one that is inhibitory. And for neural masses, these are also split into multiple. If I recall correctly, there is no abstract type beneath neural mass, so we only have different blocks that are neural mass blocks from the literature, like Wilson-Cohen or Larter-Breakspear. And in the stimulus category, we have anything that is an external stimulus into a Blox. That can be an image stimulus, as you saw in the category learning task. We can provide images that are, pixel by pixel matched to a Blox as an input. Or we can have Bloxes like the Poisson spike 10 that it does exactly what it says. It just generates spikes with a Poisson process that go into your neuron. And observer Bloxes, we'll see some of them on Friday when we talk about DCM. So these are like measurement Bloxes. These are Bloxes that represent some experimental measure. So if you attach that on top of a Blox with dynamics, you can, transform some variables in that Blox, for instance, its voltage, into something that is actually measurable in an experiment. For instance, volt signal. So here I just want to show you a couple of examples of Blox definitions, so you can see how they look like in the source code, and you will design some of these yourselves. So this is a Wilson-Cohen, which is a subtype of neural mass block, right? Using the syntax for subtyping here. And as you will see shortly in the exercises, the necessary fields for any Blox are two, essentially the system and the namespace. The params here is optional. We have it for some convenience internally in the code, but you don't really need these params. And the system field is going to hold the system of differential equations, and the namespace, we will talk more about namespace tomorrow when we talk about circuits, but this is essentially to designate where exactly in the hierarchy of Bloxes we are right now, right? Because if, for instance, this Blox is a final Blox in our graph, then the namespace is only the name of the final model. But if this Blox is hidden inside another Blox, and another Blox, then this namespace carries that information, so we know exactly where we are with each object. And we need to define a function which is essentially a constructor for our Blox, right? So we need to tell Julia essentially how to construct an object called Wilson-Cohen. So this is what this function is doing, and this is an internal constructor, and it's called internal because the function definition, as you can see, is inside the structure definition. And we do it like this, well, for convenience, and also if you define an internal constructor, then that's the default one, and that's the only internal constructor that will be used. So for instance, you cannot now define a Wilson-Cohen block by providing params and system and namespace, because we're not expecting everybody to provide these three fields as inputs to a constructor. We expect somebody to provide in all the parameters that the Wilson-Cohen block has, and you can see these are all keyword arguments. And we always stick to keyword arguments because for convenience, you have to explicitly type the parameter name and the value, so you know exactly which parameter you're setting what value. So you supply all these parameters that are relevant to your blocks, and then you would define a set of variables exactly as you did in the morning session, and also a set of parameters if needed. This is done through parameter scoping here. Param scoping is some NeuroBlox function internally to figure out if your parameters are shared with other Bloxes. So you can do that as well. Say that you have 500 of these Wilson-Cohen Bloxes, but you want all of them to have one common tau v parameter, right? This is handled internally by this param scoping function. The equations, exactly as before, you type them out symbolically using modeling toolkit syntax. And finally, you just define your system, and you supply that system the namespace and optionally the parameters in your function, in your call to this new function. And this new function is a special function for any internal constructor that basically outputs an object of type Wilson-Cohen, right? Because this function is a constructor, so at the end it's going to construct an object of this type for us. And likewise, this is the definition of an LIF neuron, a leaky integrated fire neuron. As you can see, this time it's a subtype of neuron. It's important to designate this. And again, as an input, it takes in all of the relevant parameters for the model. It passes those values to symbolic parameters here, and it defines its variables with some default values, equations, and the extra thing here, of course, is the spiking, right? because this is an integrated firing neuron, so we need to do the spiking manually, exactly how you did with the GKVS neuron in the morning. So in our system definition here, we just pass as discrete events the spiking event. And yeah, again, the same call to new. This is basically all you need to write a new Blox. Now, because neuron already comes with a lot of blocks already implemented, of course, one way of looking at them would be looking directly at the source code. If you want to do that, that's fine. But I would say an easier way, in a more user-friendly way, is to go through help. So, and this is a general Julia feature. If you are in a Julia session and you type in the question mark, then it jumps from the normal Julia session to this help. And if you type in any type, any Julia type here, it's going to give you essentially the doc string of that type, which is essentially a short documentation for that type. And we have written documentations like this for our Bloxes. So if you type, for instance, help question mark LIF neuron, then the output is this this doc string essentially, which describes what this block is, what its parameters are, and how you can construct it. So then there's also a reference, because this Blox comes from the literature. It's implemented based on a paper. So you can know more about this. So you can know more about how to use it in your code. Now moving on to connections. As I said, both Bloxes and connections have custom types, and the custom type for connections is this connector object. Essentially, every connection, every edge in our graph, right? Every connection between two Bloxes will generate a connector object, and that object will hold all information about how these two Bloxes should talk to one another. And in order to create these connectors, right, we also have constructor functions, and these constructors rely on multiple dispatches essentially to do so. And the multiple dispatch relies on the type of the source blocks, the type of the destination blocks, right? So we can have different rules that are different combinations of a source block and a destination blocks. And of course, some rules are reasonable, like connecting two neurons together. There is a rule for that. But some rules are not implemented in neuroblocks because we never expect them to be used. For instance, if you want to connect a neuron to a stimulus, that connection doesn't apply, and it doesn't exist in neuroblocks. But of course, a connection from a stimulus to a neuron exists, whether that's an Iman stimulus or a Poisson spike train or any other. Now, when you define a new Blox, sometimes, most of the time, in fact, it's enough if you subtype it as something. For instance, you define a neuron model and you subtype that as neuron, or a neural mass subtype as neural mass block. And that is enough for it to fall under some connection rule. So even if you don't define your own connection rule and you only define a custom Blox, then you should be able to interface with other Bloxes, because we have some generic connection rules. So if Julia doesn't find a connection rule specifically for your Blox, it's going to fall back to the generic one. But of course, if your case is more exotic, or you want some specific connection rule, it's easy to define your own. So then the generic one will be replaced by your own. And what you need to define a connection rule is basically essentially summarized here. Here I'm showing you again a screenshot from the NeuroBlox source code. And this is the most general definition of a connector object that takes in, as you can see, both of the source. The source block is just an abstract block. It could be any type of block, and the destination blocks can be, again, abstract blocks, anything, right? But we don't expect the user to write connector constructors like this. We expect the user to add their own dispatch to these functions highlighted here. So you have 4 functions that you can extend with your own rules. So maybe the most important one is connection rule. So if you want to write connection equations. So if you want to write your own connection equations, you can import this function. You will see how to do that in the exercises, and just write your own function definition, and that adds another dispatch for this function. So when actually NeuroBlox tries to connect your blocks with another blocks, and you have connection equations defined for your blocks, comma, and another type of blocks, then it's going to call your function. Likewise, you can add the connection learning rule. So this applies to reinforcement learning, and we'll talk about reinforcement learning and plasticity on Thursday. So if you want, those symbolic weights that get generated every time you add the connection, if you want those weights to update based on some plasticity rule, you can write that in a function called connection learning rule and extend essentially this definition. Connection callbacks can be any callbacks that you would like to add to connection. We left this blank for anything that you want to add. But there are connection spike effects, which are essentially specific callbacks that apply to spiking. And we have these separated for convenience, because you will see that connection spike effects are easier to write. And you can write them as, when this source neuron spikes, apply these equations. So again, all you need to do to write your own custom connection rule is define all or maybe some of these four functions. Sometimes, all you want is some continuous equation between two blocks, so it's enough to define connection equations. But maybe you have neurons like the Gigovich neuron, which has this event type spiking. So you want at every event to affect the destination neuron. And so in that case, you would extend the connection spike effects. So finally, as I said, because we have many neurons implemented in NeuroBlox, and actually the library is growing, there can be like a combinatorial explosion of connection rules, right? Because many of the viable pairs of blocks together can have specialized rules, right? But you as a user, if you want to see what rule applies to a couple of blocks, you can actually call this function, what's called connection rule. Here I just defined two blocks. You will see how to do this. And then I call my connection rule function, with the source neuron first and the destination neuron or blocks in general second. And then any keyword arguments, because weight here is a keyword argument that I've just given it a value of 1. And then I get a nice printout that tells me what connection am I looking at, what's the equation that applies to this connection, and any other additional things. For instance, it tells me the weights that have been generated specifically for this connection. So when this connection happens in the model, I'm going to get a symbolic parameter generated that is called weight underscore W underscore the name of the source neuron underscore the name of the destination neuron. And we made it so that these weights are easy to find. So maybe you want to print your weights in the end, especially if you're doing learning. So they're easy to find like this. But also this specific connection, because it's LIF neurons and they have this event type spiking, also includes some spike effects, right? And you also get a nice print of these. So the print tells you that each time LIF1 spikes, then it affects the specific state on LIF2. So it affects the AMPA channel of LIF2 by incrementing it by the symbolic weight, basically. But this function applies to any combination of blocks. So if you're uncertain about what's the rule connecting these two objects together, you can call this. And if you're unsatisfied by the answer, maybe you can write your own rule. And this was the end, essentially. So yeah, exactly like the morning session. But from now on, it's going to be a single notebook per session. Yeah, you can just navigate to blocks and connection in NeuroBlox. This is essentially the page, exactly like the notebook. And the notebook name is the blocks connections here. So yeah, please open the notebook. And if you have any questions about the talk, feel free to ask now. Otherwise, you can start with the exercises and yeah, ask us anytime.